Here we go. Let's talk about these. Let's see what you came up with. So how about right here? Yeah. Yes, you. All right, hold on. So what did you talk about? The general idea of the divergence theorem? No, right here. This young lady, right here. Okay, she said that the series cannot converge unless the sequence converges to zero. What do you think about that? Couple nods. Okay, yeah, the general idea is if your sequence doesn't go to zero, the series will diverge. If the sequence doesn't go to zero, the series could never converge. It diverges. That's the idea. The flip side is kind of more what she said. The flip side is if the sequence goes to zero, then we've got a chance. You're telling me there's a chance, right? If the sequence goes to zero, then the series might have a chance to add up to a finite number. Is it guaranteed? But still not guaranteed, right? So it's necessary that the sequence converges to zero in order for the series to converge, but not sufficient. All right? Okay, the harmonic series over here. How about right here, the black hat? In the black hat, right there. Yeah. I got the list of names is coming, so it'll be a lot easier. Here we go. Okay, the harmonic series is 1 over n. What about 1 over n? Right? Okay, well said. So the only little thing was, you said the harmonic series is 1 over n. Is it 1 over n? This is kind of technicality here. What is a series? Sum, right? So it's a sum. All right, so we're going to sum up the sequence, 1 over n. That's the series, okay? And yes, so she said that, how does it relate to the divergence theorem? So that sequence goes to zero or not? The sequence, right? The harmonic sequence goes to zero. But it's right. So the series has a chance, but for this one, no. It doesn't get to zero fast enough. So you add up those terms, and we showed by comparison that it still adds up to infinity. Even though that sequence is going to zero, it kind of hovers too high, too long, right? Those values stay too high, too long, and when you add them all together, it can get as big as you like. Okay? How would we use comparison to show convergence? How would you use comparison to show convergence? Yeah, Griffin. Yeah. Okay. Convergent series. Yeah, so well done. So he said if you have a known convergent series, right, you add them up and it adds up to a finite value. And then the series you're looking at, all its terms are how compared to the terms of the one you know. All less than or equal to. So if the one you're analyzing, all of its terms are less than or equal to one you know sums up to a finite value, then the one you're looking at has to sum up to a finite value also, right? Should make sense. What if you have one that sums up to a finite value, right? And then yours, they're all greater than it. All your terms are greater than it. So is it divergent then? Unknown. It still could be convergent or divergent, so no conclusion. Okay? All right. What's a geometric series? Right here.
So the sigma a r to the n-1.
Okay. When r is? Okay. Yeah. So when r is between -1 and 1, that thing will sum up to a over 1 minus r. And when it's r values other than that, what can you say about the series? So if r is -1 or 1 or outside of that range, boom, divergent, right? The geometric series can diverge. So what is the idea? Okay, so what's the idea behind the geometric series? Well, we talked about this last time. So what's going on in those terms in the geometric series? Volunteer? Remember? Yes, sir. Yeah, right. To get the next term, you just take the last term multiplied by r, right? Because it's r to the, power of. So whatever term we're on, we're multiplying by a number of r's related to where we're at, right? So the next term will have one more r multiplied to the last term. So if we keep multiplying by r and it's outside of 1 or -1, then these terms are blowing up, right? These terms are blowing up, okay? Because you keep multiplying by a number greater than 1 or less than -1. Okay, any questions on this review discussion? All right, let's take a look briefly and see if there was any trouble on the web work. Oh, look at that, number 2. Perfect. Okay. All right, so what do we got here? -5/9, 25 over 81, etc. Okay, so we got, let's label the terms with n, right? So this is going to help us. So we have to kind of come up with the ar to the n-1 form for this, knowing that it is indeed geometric, but you knew that because the name of the set was called geometric series. Okay, but we need to come up with ar to the n-1. So when n is 1, we get -5/9. When n is 2, we get 25 over 81, etc. Okay, so the whole key is the r is the value we multiply the last term by to get the next one, right? What is it we're multiplying by every time to get the next term? Yeah, -5/9, right? So -5/9 times -5/9 is positive 25 over 81 times -5/9 is that. Okay, so we know for sure r is -5/9. But then we got to make this work so that when n equals 1, we get -5/9. So the way it is now, hold on a sec. The way it is now, if I just have it like that, when n equals 1, do I get the first term to be -5/9? What would I get? Not 1. I guess 1, yeah, because the exponent is 0, right? So the exponent would be 0. So in this case, n equals 1 would give me the value 1. And n equals 2 would give me the first term. All right? So how can I fix that? So I need n equals 1. When I plug 1 into this, I need to get -5/9. Right now, I just get 1, because it's -5/9 to the 0. So what would I need? I just multiply it by another -5/9 out here, right? And now we should check, though. Check. So like look at the second now. When n equals 2, what would we have? When n equals 2, we have -5/9 to the 1 times -5/9. And is that what we have? Positive 25 over 81. Yeah. Okay. So then we've got geometric. We know this is ar to the n-1. And then does it converge or not? Yes, because this is in our range of -1 to 1. So we're good. And so what does it converge to? A over 1 minus, and what's r? Negative. So is that a over 1 minus r? Just follow it literally. Even though there's negatives in there and this thing is flip-flopping, it's still, this still produces exactly that series. It's a r to the n-1, so it's literally a over 1 minus r. Okay, questions on this example? Okay, so this series is an example of what's called an It's a nice lead-in for today's subject. This is called an alternating series. We had alternating sequences, didn't we? Yeah, we talked about alternating sequences. So what, by alternating, we mean that as you go from term to term, the sign alternates, positive, negative, positive, negative, positive, negative. So here's this particular geometric series by having a negative value of r will give you an alternating effect, right? It'll, because whenever you multiply an even number of those together, that will be positive. In this case, then you end up with a negative. And then whenever you multiply an odd number of negatives together, you get a negative. So by continually having these exponents, go up by the whole numbers, then you're going to get even, or positive, negative, positive, negative. You're going to get even, odd number of r's multiplied together. Okay, so let's define an alternating series generally. So some geometric series are alternating. If r is negative, it'll be an alternate. It'll alternate. Oh, before we do that, we need to just define. We didn't quite define p series. So p series is of the form. It's just summing up a p sequence. Is it 1 over p to the n or 1 over n to the p? So remember, when n is in the exponent, that's what kind of series? When n is in the exponent. That's our geometric. So the p series is when the n is in the base, right? The number that changes in the base, and the p, the one that stays the same, is the exponent. That's the p series. And so what did we find out last time? And so we know when p equals 1, what do we have? Well, what is it? So when p equals 1, what series do we have? 1 over n, right? And that's the harmonic series. So the harmonic series is just a particular case of a p series, right? It's the case when p equals 1. It's the case when p equals 1. All right, so, and we found we found out that converges or diverges? Diverges. And what about if that p is then less than 1? We showed like square root. Yeah, because then all those terms will be, if you have a p less than 1, like 1 over square root of n or 1 over n to the 1/3, then every single term will compare how to 1 over n? Larger, right? So for instance, even like 0.8. Okay? Every one of those is bigger or smaller than each one of the 1 over n's? Bigger. That's a bigger value than that for every n. And since this one diverges, that's got to diverge too. That's comparison. Divergence by comparison to one that we know. So when does the p series converge? It converges when? So actually, it turns out the harmonic series is the cutoff. Okay? The harmonic series is the one with the lowest values that still diverges. So as long as that exponent is a little bit greater than 1, then it gets to 0 fast enough for the sum to converge. Okay? So this is kind of the first value of p where it blows up in terms of heading down in p, right? So any value of p greater than 1, so 1 over n to the 1.001. So p equals, so these are both divergent, right? P equals 1.001, 1 over n to the 1.001. All these terms are how compared to the terms of the harmonic series? Bigger or less? 1 over n to the 1.001. They're all a little bit less, right? You got a bigger denominator, and you're taking 1 over a slightly larger denominator. So all these terms are slightly less, and since 1 over n is the cutoff, all it has to do is be inside of the harmonic series, and it's going to converge. So this converges. In fact, any p greater than 1, you'll have converged. Now it'll converge to a really, really big number, okay? Because it's going down so slow, but it will eventually converge. Okay, so that was a summary we should have done last time, and now you've got the homework for the second web work. I hope you noticed it's due Friday and it wasn't due today. All right, so yeah, any questions on the P series? Diverges when P is less than or equal to 1, converges when P is greater than 1. Okay. All right, so alternating series is of the form so it could be n or n plus 1. I'm just making the first one positive, but that could be n or n plus 1. Negative 1 to the n plus 1 or negative 1 to the n, doesn't matter. All right, so we're going to extract out the alternating part, and so then where Bn is greater than 0 for all n. So I've got, what do I have? I have a sequence that has all positive terms, and I'm going to force that thing to alternate by doing negative 1 to the n plus 1. So like that one that we had, how could we make that geometric series look like this? So we had what? Negative 5/9 times negative 5/9 to the n minus 1, right? So how can we make it look like this form? Well, so what we need to do is see that this is the same as, we really want that 5/9 to be to the n minus 1, positive. So that means that every one of those, right, we're going to do so I'm just gonna pull that negative 1 out. So it's negative 5/9 to the n minus 1. I just pull out the negative 1 and make it negative 1 to the n minus 1 and 5/9 to the n minus 1. So it's kind of like I'm factoring out a negative 1 from every single negative 5/9 that I have. So it's going to be n minus 1 of them, right? Okay, and then if I want to keep going with this, yeah, so that would be fine the way it is. Another thing we could do would be to do negative 1 to just the n, and so then it's like I'm taking one of those negative 1s and combining it with a negative 5/9 to make positive 5/9, and then 5/9 to the n minus 1. And then if I wanted, that would just be 5/9 to the n, right? Because n minus 1 5/9 and 1 more 5/9, that I could simplify that further and just say 5/9 to the n. Okay, but the reason that we had that separated out was for our form of the, we knew we needed a times r to the n minus 1. That's why we had it separate before. So I'm just showing you some rules of exponents here. I can change some things around. So, so now this fits that form of an alternating series. We got the alternating effect, -1 to the n or -1 to the n plus 1. And then in this case, all positive terms now, bn would be the rest of it. That's a positive sequence. Okay, the 5/9 times 5/9 to the n minus 1. Okay, so the alternating series test is this. So it's a test for convergence. So when does an alternating series converge? Two things. If so I say if bn plus 1 is less than or equal to bn for all n. What does that tell me about the sequence? What am I, in a nutshell, what is that saying about the sequence? That what the next term is less than or equal to the previous term. What does that say about the sequence? The values of the sequence. Yeah, the smallest. This is a decreasing sequence, right? This is a decreasing sequence. And that sequence goes to 0. Okay? So what do we need? We need a decreasing sequence that converges to 0. If bn is any decreasing sequence, and we already said it was positive, so if it's a decreasing sequence that converges to 0, then this thing converges. Does that remind you of anything we've talked about before? What does that remind you of? This says, if you have a sequence and it goes to 0, basically, if it goes to 0, it converges. What's that? Okay, so what did the divergence theorem say? Is that what the divergence theorem said? That if you have a decreasing sequence to 0, it converges? What did we say about that? So the jury's out. We don't know for sure. So why can we say it now? What's different? This is just saying that you have a positive sequence converging to 0, right? You have a positive sequence decreasing and converging to 0. I thought that wasn't enough, right? Didn't we say that wasn't enough? So what's going on here? What's different? Yeah, so this, now we're talking about an alternating series. So how does that make a difference, right? So we didn't have this before. So the bn part is positive and decreasing to 0, but the series itself still has this part to it, right? Where the terms flip-flop and alternate in their sign. Positive, negative, positive, negative. So why does that make a difference? What's that? Right, exactly. So half of your terms, half of infinite limiting terms are now negative instead of positive. This is going to help, right? This is going to help when you're adding a bunch of things up. You're adding a bunch of things up. If half of them are negative, then every time you add a negative, it's going to help. The sum's going to go down a little bit. So the difference is that you've got this alternating effect. So with the alternating effect, now it's sufficient that your sequence just goes to 0, the positive part of it, right? just the sequence without the alternating. As long as that goes to 0, throw the alternating on it, and you got it. That's what the alternating series test says. You got a convergent series. Okay, so let's talk about that a little more here. So let's talk about how about this? So what would we call this? What would we name this? Alternating harmonic series, the alternating harmonic series. Convergent or divergent? Okay, so the harmonic series is divergent, but is this convergent? By what we just said, right? Because it meets the criteria for the alternating series test. This is what? All positive terms that decrease and converge to 0, the sequence. Throw the alternating effect on, and now converges. So let's see this happen. So first of all, I want you see this, think what, right? See this, think what? Go. See this, think what? Write it down. Okay, let's see here. How about back there in the gray t-shirt? Forgot your name, yeah? So what does this mean literally? When you see this, what does it mean literally? So is it a list? It's a list. Sum of the list. So what is it? Tell me, what is it? Okay. Which is 1. Minus 1/2. Plus 1. Third. Etc. Right? Is that what you guys wrote? Okay. So this is the alternating harmonic series. So let's see what happens here. So let's keep track of the partial sums, right? Partial sums is like, remember the sequence of partial sums? What would that be? So the first partial sum is for just n equals 1. And what is that? 1, right? So if we think about the first partial sum is just the number 1. It's just the first term. 1 takes us to here on the number line. That's 1, okay? What is the second partial sum? The second partial sum is where we add the first 2 terms together. What is it? 1/2. So now, it's like we're going to go back by 1/2. So we're going to subtract 1/2, and that's going to end up, we're going to end up at S2. So S2 is 1/2. Second partial sum. And what are we going to do next? We're going to add a third. So what is the third partial sum? One half plus a third is 5/6. So we're going to go up a third. And so S3 will be 5/6. See what's happening? Next, we're going to subtract a fourth. I don't know, I can't do that in my head. Whatever 5, 6 minus a fourth is, so we're going to go back a fourth. And that will be S4. So do you see what's happening? You keep adding one more, it keeps what? It's just going to keep honing in on there's going to be some limiting value here. We're going to, S5 will be like this, S6, S7, as we add, then subtract, then add, subtract smaller and smaller numbers. It's going to converge to something here. Okay, so we're not going to talk about how to get that convergent value exactly, but how could we kind of figure out what it might be? How could we just kind of get an idea of what it is? What that number that it's converging on is? What could you do? So that would be some kind of idea, but we could do a lot better than that. We could do a lot better than that. So yeah, it's true. It's going to be somewhere between, and given any two adjacent, it'll be between those two. But I'm going to do better than that. I'm going to get a really good approximation. Not about an average. It's not about an average. No. How could we just get a really good estimate? Okay, well the sequence of partial sums is going to give me the exact value, but you're on the right track, right? You're on the right track. What could I look at to get a really good approximation? Just look at a partial sum that has lots of terms, right? What's happening to these terms? Each one of these terms is getting smaller, right? So we keep changing that every time we add another term, we're changing it by a smaller and smaller amount, right? So if I just take enough terms, so I take 100 terms, it's going to be really, really close, right? Because the ones after that are going to be really small numbers that we're changing it by. So yeah, because the sequence is going to 0, the further you go down the series, the more terms you take, the closer and closer the value is going to be to the convergent value. So just look at, say, S20. And that would be a good approximation. It will be off by, what will it be off by? The 21st term, the sum from the 21st term on. That's what will be the error, the rest of it, right? Okay, so S20. Or maybe S10 would be, good enough if you just wanted it to 1 decimal place or something like this. Maybe S10 would be good enough. S20 will be even better. S100 will be a really good approximation of the sum. Okay? That should be what, within, close to within 100th or something. All right, questions on, so this is the idea of an alternating series. And why, and why it converges, right? Why does it converge? The only thing that has to happen now is that what we said before wasn't enough, right? That sequence just needs to go to 0. Throw the alternating effect on there, and you got a convergent series. Okay, so let's talk about absolute convergence, okay? So a series is absolutely convergent if the sum of the absolute value of the terms is convergent. So what's the idea? So what's the idea of taking the absolute value of every term? Taking the absolute value of every term means removing the alternating effect, right? We just talked about alternating series. So by doing that, you remove the alternating effect. You make them all positive. If it still converges after that, then you've got an absolutely convergent series. Meaning, It's not dependent on the alternating effect to help it converge. It can do it all on its own without the negative, positive, negative, positive. Okay? The alternating harmonic series, is it absolutely convergent? So, what do? We test the version of that alternating series where all the terms are positive. So, look at, what do we look at to ask if it's absolutely convergent? We look at what series would we look at? What happens to the terms if I just slap a alternating or a absolute value on each term? What does it end up being? Just the harmonic series, right? So we look at that, which is divergent. So is the alternating harmonic series absolutely convergent? No. It depends. It needs that alternating effect in order for it to converge. So therefore, it's what we call conditionally convergent. Condition. You need the condition of the negative 1 to the n plus 1, or the negative 1 to the n. You need that condition on there in order to allow it to converge. If that's gone, it diverges. Therefore, it's not absolutely convergent. It's only conditionally convergent. Okay? Does that make sense? Okay, what about alternating 1 over n cubed? Is that absolutely convergent? What do you look at? So, we look at what series would we look at to test to see if that one is absolutely convergent? 1 over n cubed. Convergent or divergent? Why can you conclude it's convergent? P series, P is greater than 1. Therefore, the original series we were looking at, the alternating series, absolutely convergent. It converges whether you have the alternating effect or not. If it's there, great. But it didn't need it in the first place. 1 over n cubed, it gets to 0 fast enough, it converges on its own. So therefore, this is like the strongest convergence. Absolute convergence. Okay, so whenever you have written homework or on the exam or quizzes, you have to justify. You can't just write down answers with these. Okay? So this is an example of a good solution to this. You have to show all your work and show all your justification. Okay? So to show absolute convergence, we're going to look at the series where all the terms are positive. We convert that to convergent P series. Why? Because P is greater than 1. Therefore, the original series is absolutely convergent. Okay, questions on that? Okay, so we have a test for absolute convergence. So some easy ones like this, we can just analyzed this way because it was easy. We knew it had related to P series. But then we've got more complicated series they're not just geometric or not just a P series. And we have a test for absolute convergence, and it's called the ratio test. Okay, so just listen for a sec first before you start writing down. And we'll take time on Friday to kind of talk more about the idea behind this, but let's just state the test. So given the infinite series, we're going to evaluate this limit. And then so we're going to form a new sequence, right? So we're going to take a new sequence, which is the ratio of the n plus first term to the nth term. We're going to set up this ratio and take the absolute value of that ratio. And then we're going to look at that. That's a sequence, okay? That's a sequence of values. And now we're going to analyze that sequence. We're going to analyze whether that sequence converges, converges, diverges, and if so, converges to L. Depending on what L is, depending on what it converges to, then we can make different conclusions about that original series. So if L is less than 1, then the series is absolutely convergent. Okay? If that sequence that we form converges to a number less than 1, we've got an absolutely convergent series. If it's greater than 1, the series is divergent. And if L equals 1, then it's no conclusion and we have to use something else. If we wanted to keep analyzing that series, we have to use something else. It's not going to help. Okay, so just one example. Oh, that's for, okay. So that we're going to set up this ratio of the n plus first term to the nth term. All right, so what is the n plus first term? Well, it's going to be negative 3 to the n plus 1 over n plus 1 cubed. That's a n plus 1, that whole thing, right? So looking at a sub n, I'm just going to substitute n plus 1 in wherever there's an n. All over n plus 1, negative 3 to the n over n cubed. And now I'm going to simplify this ratio and analyze that sequence. So I'm going to invert and multiply. And from here on out, you can just do that from the start. Because lots of times these are given as fractions. So you can just start with this step right here. There's a n plus 1. Instead of dividing by a n, we'll multiply by the reciprocal. And so that's normally where we will start these problems, to save that step. I just wanted to show you that the first time. Okay, so now we got the sequence. First of all, negative 3 to the n, negative 3 to n plus 1, it's just a negative 3. Almost done. So right, this is n plus 1 negative 3's, and that's n negative 3's. That leaves one more negative 3 on the top. Right? There's one more negative 3 multiplied than these. And then we have over n cubed plus 1. N plus 1 cubed. And now we have to know our sequences. So the negative 3 is just going to become positive 3 in the absolute value. What does that approach as n goes to infinity? No. So in your leading term at the bottom will be n cubed. So we really have n cubed over n cubed. Remember sequences? Goes to 1, right? So this is going to equal negative 3 times 1 or 3. Conclusion? That's greater than 1. Divergent sequence. Series.